In this video, we'll be covering section 10.4, the hyperbola. We have 4 objectives. We will be analyzing hyperbolas centered at the origin. We will find the asymptotes of a hyperbola, and then we will analyze hyperbolas that are centered at a point that is not the origin, and we will finish by looking at applied problems involving hyperbolas. If we recall, all of our conic sections were defined as cross-sections of a cone, and the hyperbola was constructed where we took a plane and we sliced through the cone so that the plane was parallel to the axis. Remember, this up here is the axis for that cone. You could also think of it as the plane is perpendicular to the circular parts that you see here. So the cross section that you get, this part here with the branch down below it, that was where we get our hyperbola. Okay, so all of them were defined in this way, but we also had more strictly geometric definitions, and the hyperbola is the same. So its definition, it says a hyperbola is the collection of all points in the plane, the distance of whose distances from 2 fixed points, called the foci, is constant. Okay, so that's a mouthful, so what is it saying? Well, imagine we take a point that we say is on the hyperbola. We then find the distance between the focus and that point, let's call it P, and then we find the distance between P and the other focus. If we subtract those two, so the way we'll write that as distance between F1 and P minus the distance between P and F2, that's always some constant, some number that doesn't change. So no matter where I move that point, this segment minus this segment is always the same number. So for example, if I pick a point down here, if I measure the length of that segment, subtract the length of that segment there, it will give me the same constant that we have here. And you can go on the other branch as well. So I could pick this point, I could measure this distance and this distance, subtract them, take the longer one minus the smaller one, and you will get this same constant. So very similar to what we saw with an ellipse. With an ellipse, it was that the sum of the 2 points was constant. With a hyperbola, it's that their difference is constant. Okay, some terminology for an ellipse. Let's erase some of this. So first is transverse axis. The transverse axis is the line that passes through both of the foci. So this is analogous to the major axis for an ellipse, but for an hyperbola, it's called the transverse axis. Then the center is simply defined to be the midpoint between the 2 foci. So here's our center point. That's equivalent to what we had for an ellipse. The center for an ellipse is the midpoint of the foci there as well. The conjugate axis is the line that is perpendicular to the transverse axis passing through the center. And then the vertices are the points where the 2 branches intersect the transverse axis. Okay, so our goal is to come up with a formula for the hyperbola, but we need to get some notation before we do that. So the first thing that we're going to do is we're going to define the foci to be at C0 and negative C0. So we're starting with the case of the center being at the origin. And basically what we're really saying here is that the distance from the center to the focus is C. And that is going to be the convention that we always are going to use. C will always represent the distance from the center to the focus. This is consistent with what we did for ellipses. If you have an ellipse, your foci are inside, but we still defined this distance to be C. So that is consistent here. We're also going to define the distance to a vertex to be A, which is also consistent with an ellipse. We used A to denote that distance from the center to the vertex. So those 2 pieces match. What's different is that with an ellipse, the value of C is always less than the value of A. Whereas with a hyperbola, the value of C is always bigger than the value of A. So they switch sizes here. Okay, so let's come back to the definition. And so what we're going to look at here is we're going to analyze this specific point right here. So that point is on the hyperbola. If it's on the hyperbola, then it should fit the definition. So what I mean by that is the distance from this focus to that point minus the distance from that point to this focus, if I take the difference between this orange segment and this green segment, I have to get a constant. Now, given the way that we've labeled everything, let's write down what that constant actually comes out to. So right here I've said we're going to do the distance from F1 to V2. That's this orange segment. We have defined the distance from the focus to the center to be C. So just this part of it is C, and we also defined this part of it to be A. So this initial distance from F1 over to V2 is C plus A. So I've just replaced that right there. This distance is C plus A. Then the other distance, the distance from F2 to V2, is this green segment. Well, that distance would be all of this minus this part, right? You would take the whole thing and then just subtract this piece here. Well, the whole thing is again C. Distance from the center to the focus is C, and this smaller piece is just A, which means the green segment would be C minus A. The distance from this vertex to this focus would be C minus A. Okay, so we've put that there. We need to subtract these two things. If we subtract them, then we end up with 2A. Notice that this is also consistent with what we had for an ellipse. For an ellipse, it was that the sum of the 2 points was always 2A, but it still ends up being the same thing here. The difference is always 2A. It's always twice the difference, twice the distance from the center to that vertex. Okay, so using that fact, we can then derive an equation for an ellipse. Now, I'm not going to make us go through every step like I did for the previous one because most of this is the same. We start off with that distance formula that we just had a second ago. We said that no matter where the point is, we looked at this point, but it's true for any random point. So I'm just picking a point xy here. And this equation should still be true. This distance minus this distance should be 2A. Now you notice I have a plus or minus here, and that's because we don't actually know ahead of time which one is the longer segment. So it could come out positive or negative, depending on if we took, the shorter minus the longer one would be the negative, longer one minus the shorter one would be the positive one. It won't matter, this plus or minus is going to get wiped out in a second anyway. Okay, we plug it all into the distance formula, and then we start solving. And the process of solving it is exactly like it was before. I have a bunch of expanding, FOIL things out, move things to one side, square it again. So we won't go through every step there. I'll let you read through that. But eventually, we start canceling things and rearranging things, and we get to a similar place that we did for the ellipse. And that was an equation that looked kind of like this. So it's almost identical, but you have a different sign right here. So at this stage, we're going to make a definition. We're going to define c squared minus a squared to just be a new number, b squared. Just redefining this to be equal to b squared. So we just replace those with b squared. Now this is an important fact. It's going to come back later. If I reordered this, this would say c squared equals a squared plus b squared. This is something that is always going to be true for a hyperbola. We'll see how that's actually useful. This highlights another place where hyperbolas are different from ellipses. With an ellipse, it wasn't this, it was a squared was always equal to b squared plus c squared. Right? That was true for an ellipse. But for a hyperbola, this is the relationship that we have. Okay, so we'll come back to that, but we just replace those with the b squared in those two places, and then we finish it by dividing everything by a squared b squared. Each term divided by a squared b squared. And then you get a bunch of cancellation like we did before, and you end up with this equation here. And you can see very, very close to an ellipse. The only difference is this is a minus sign here, whereas with an ellipse it was plus. So it's kind of nice that it works out that way. Very similar. But then we get this relationship. So there are two main differences. You have a minus sign here, and then we have b squared equals c squared minus a squared, rather than having a squared equal to b squared plus c squared. So I don't typically use this form though. I think for me it's easier to remember the c squared equals a squared plus b squared. Even though we're typically going to be solving for b, this is the way I remember it. So with an ellipse, I always remembered that a squared was equal to b squared plus c squared, and then solved it for whichever one I needed. And I'm going to use this for hyperbolas. Okay, so this gives us the equation when it's centered at the origin, and also when the conjugate axis is not intersecting the hyperbola, meaning the conjugate axis is the y-axis, transverse axis is the x-axis. So this is another important thing we're going to have to remember here. Transverse axis is always going to be the first term here, the one that's not the negative one. Okay, another big difference is that we've kind of mentioned before, but I want to address it again. Back when we did ellipses, A always represented the bigger of the two numbers. That is not true here. A could be smaller than B, and that's coming from the fact that C is always bigger than A. And so given this relationship here, we can't actually say which of these two is bigger. So we have to forget that. The A is always going to go with whichever term is in front here for this one. So the A is always the positive one, and the B squared goes with the negative one. Okay, let's try our first example. It says find an equation of the hyperbola with the center at the origin, one focus at 3, 0, one vertex at negative 2, 0. We're going to graph that equation. So let's start with the points. We've got a point here, 3, 0, that is a focus. And we have a vertex at negative 2, 0. And then it also said that the center was at 0, 0. Okay, so this gives us quite a bit of information already. The distance from here to the center, from V to the center, that is A. So we know A is equal to 2. We also know that the distance from the center to a focus is C. So that tells us that C is equal to 3. Then we can use the fact that C squared is equal to A squared plus B squared to help us get the value of B. So B would be equal to the square root of C squared minus A squared. In this problem, that is 9 minus 4. So it will be square root of 5. And that is approximately 2.24, I believe. Okay, so if we want the equation, we know that this has the form of x squared over a squared minus y squared over b squared equals 1. I guess we should put in the other vertex. So the other vertex would have to be here. So if that's V1, this would be V2, and we can put in the other focus as well. So it would just be back at negative 3. This would be F1, this would be F2. So we know it's this form because it's centered at the origin, and the transverse axis is the x-axis. So that's what tells us it's in this form. So then we can just put in all the information. So we will have x squared over a squared, which is 4, minus y squared over b squared. Now don't use the decimal, square this, which would just put a 5 there, equals 1. So that's our equation. Pretty easy to get to that point. So we want to graph this. Now, unfortunately, the graphing of hyperbolas takes a little bit more work. We know that it passes through these two vertices, but we don't have any other points at this moment. So to get the other points, what you need to do is just pick an x value and plug it into this equation to get y values to go with it. And the book, most of the time, they use the x values for the foci. So what we're going to do is we're going to say, suppose x was equal to either plus or minus 3. We're actually going to plug in both of those at the same time and see what the y values are. Now the reason we can plug in plus and minus at the same time is it immediately gets wiped out. Right? You're going to have plus or minus 3 squared over 4 minus y squared over 5 equals 1. So that negative that would be in there would get wiped out. So 9/4 minus y squared over 5 equals 1. If you don't want to deal with fractions, then go ahead and just multiply by the least common denominator of each side, which would be 20. If we multiply both sides by 20, you're going to get 45 minus 4y squared equals 20. Subtract the 45 over, so you're going to end up with negative 25. And then divide by negative 4, so you get y squared equals 25 over 4. Then take a square root. Don't forget, it will be plus or minus. And this one is a perfect square, so you end up with plus or minus 5 halves, which is plus or minus 2.5. So what we've done here is we've established 4 different points actually that are on the parabola. So I'm going to try on the hyperbola. I'll write them up here. So we have, if you plugged in positive 3, you could get out positive 2.5, or you could get out negative 2.5. Right? Plugging in 3 gives you either one of those. But plugging in negative 3, same thing. You get both of those options. Okay, so that gives us additional points to graph here. So we're going to go up 2.5. We're going to go down 2.5 from that point, that focus point. Then go up 2.5 here, and down 2.5, and then connect those points together to get your hyperbola. All right, and I think that's all they asked for on this particular example. These points probably would be best to label them, at least a couple of them, just so that we know exactly where they came from. We want to try to have non-rounded values in there for those when possible. Okay, so that completes our first graph and first equation. So let's move on to the next one. Okay, so similar to the last section, when the problem says analyze the equation, it is saying you need to identify the center, transverse axis, vertices, foci, and then also graph the equation. Okay, so let's give that a try in this example. So first thing we should notice is that this is in the form x squared over a squared minus y squared over b squared equals 1. So that means that a would have to be equal to 4, since 16 is a squared. B is equal to 2, since 2 squared would give you 4. We also can find c, because we know that c squared is equal to a squared plus b squared. So c will be equal to the square root of 4 squared plus 2 squared, which is the square root of 16 plus 4, or the square root of 20. We can simplify that. This could be written as square root of 4 times square root of 5, which is 2 square root of 5. That is approximately 4.5. We'll only use the decimal when we get to graphing the points. Now, since it is in this form, we know that the center has to be the origin, and the a value tells us where the vertices are. So center's at the origin. We also know, I guess we can put it in here, the transverse axis. Since the x term is the first term here, it's the one that's positive, the transverse axis has to be horizontal. Has to be, in this case, the x-axis, or you could write it as y equals 0. So that means the vertices and the foci are along this line here. So as I said, the a value tells you the distance to the vertex. So that means we will have a vertex here, and we can go back 4 as well. And then the c value tells you where the foci are. So go over about 4.5. That would be a focus, and this would be a focus. Oh, I used the same subscript on that one. Okay. Then, in order to be able to, I guess we should write down those things first too. So it says vertices. We said that they were at 4, 0 and negative 4, 0. Foci are at 2 square root of 5, 0, and negative 2 square root of 5, 0. We want the exact values there. We don't want to use any of the rounded values. All right, so I believe we've identified all of the important things. We've got the center, transverse axis, vertices, and the foci. So all of that important stuff is here. So now we want to be able to graph it. So in order to graph it, we need additional points. So similar to the previous example, we are going to plug in the foci, the x-coordinate for the foci, to get points above and below. So for this one, that would be x equals plus or minus, and I'm actually going to keep it as square root of 20. You'll see that when we plug it back into this, it's easier if you just leave it in that form. You obviously do not want to use the decimal, and you could use this, but it's easier to just use the square root of 20. Okay, so when we plug that in, that's going to give us plus or minus square root of 20 all squared over 16 minus y squared over 4 equals 1. The square is going to cancel the plus and minus, and it's going to cancel the square root. So you just have 20 over 16 minus y squared over 4 equals 1. You can reduce that fraction. So they're both divisible by 4. That just becomes 5/4 minus y squared over 4 equals 1. We can get rid of the denominator by multiplying everything by 4, which just gives us 5 minus y squared equals 4. Subtract the 5 over, negative y squared equals negative 1. Cancel the negatives, y squared equals 1. Take a square root, but don't forget you're going to get a plus or minus 1. So this actually gives us 4 different points that we can plot. What we have, and I'm going to write them down with the decimal here instead of with this. So we plugged in approximately 4.5 for the x, and what we got out was either positive 1 or negative 1. Just going to keep them together like that. But the same is also true for the negative 4.5. All right, so that tells us if we go to the focus, we can just go up 1 unit, get another point, go down a unit, get another point. Then same thing over here. Now for this particular example, these 3 points that we need to connect, they're really quite close together. So it might be better for us to try to find a different point. So to do that, okay, so I went ahead and plugged in plus or minus 6 into the equation just to see what I got out for the y values on that. I skipped the work here, but it comes out to plus or minus square root of 5. So just putting these in will give us a little bit better, just more information to get a better picture from it. So that's true on both sides. Okay, so then we just connect the points. Okay, so that's our graph. I would expect the foci to be labeled since they are not exact values, they are approximate values. So they were actually labeled over here, so that really should suffice. As long as they're written down here, we should be good. All right, so let's try a different example. So before we do the next example, what we want to look at is what happens when the transverse axis is the y-axis instead of the x-axis. Well, in the equation, what happens is these two terms just swap places. And so the minus the subtraction goes with the x squared rather than with the y squared. Notice that the first term is still divided by the a, because this still represents distance to a vertex. So it has to stay with that first term, and we still have the same relationship here. This still says that c squared is equal to a squared plus b squared. So let's try that. Okay, now before we can do this one, we do need to put it in standard form. Standard form requires that we have a 1 on the right hand side here, and that these have coefficients of 1. So to make that happen, we're just going to divide all of the terms by 4, which gives us y squared minus x squared over 4 equals 1. Now, when it's in this form, we can identify the a squared. A squared is what would be divided by the y, which means it's just 1. So that means a is 1. B squared is 4. So then b is equal to 2. We can get c just like we've done in the previous problems by taking square root of b squared, a squared plus b squared, that is. So if we plug that into this, that's square root of 1 plus 4, so square root of 5. You're going to see square root of 5 show up a lot in these problems. So about 2.24 again. Okay, so we need to identify the center, which is still the origin. Right, in this form, the new form, it's still centered at the origin. We haven't looked at examples that have been shifted yet. And but we do know the transverse axis is now the y-axis, because the positive term is the y term, and so we could write that as the equation x equals 0. All right, we can do the vertices. So if this is our center, the distance to a vertex is a, so we would just go up 1 unit to get to a vertex. We could go down a unit to get to the other one. Then to get to the, I guess we can write those down. That is 0, 1, and 0, negative 1. Okay, then the foci, we use the c value to get to the focuses. So up 2 1/4, down 2 1/4. All right, so that would be 0 square root of 5, 0 negative square root of 5. And so now we just need to get the other points. So like the previous problem, we're going to plug in square root of 5, but this time we have to plug it in for y and see what the x coordinate is. So if y is equal to, we're going to do both plus and minus square root of 5, what do we get? When we plug into this, you're just going to get 5, or 5, because the square cancels the square root, and it cancels the plus or minus x squared over 4 equals 1. So again, I'm going to multiply everything by 4 just to get rid of this fraction. So 20 minus x squared equals 4. I can subtract that over. Negative x squared equals negative 16. So x squared equals positive 16. X equals plus or minus 4. So this is giving us 4 points. It's saying if the y value is approximately plus or minus 2.24, then the x coordinate is going to be plus or minus 4. So going here, right here, go to the focus. We can go 4 units to the right, keeping the y value the same, 4 units to the left, keeping the y value the same, and then go down here, do the same thing. And then we can plot those points, or connect the points. All right, and it looks like I think we have everything. I think we analyzed the equation, have all of the information here. Oops. And we have it graphed as well. Now, one thing I want to point out, a lot of people, when they look at the picture, they say, oh, a hyperbola is just a parabola with 2 branches. But we can actually see that that is not true. And the way we can see that is if we remember in a parabola, the a value was this distance. It was the distance between the vertex and the focus. And we had what was called the lattice rectum, which joined the focus over to the 2 sides of the parabola. And for it to be a parabola, if this was a, then this entire thing had to be 4 times a. Or in other words, it had to be 2a on each side. And we can see this is much longer than 2a. So while the shape kind of looks like a parabola, geometrically it's not actually a parabola. Hyperbolas and parabolas are different things. Geometrically, their curves have different properties. Okay, next example says find an equation of the hyperbola that has one vertex at 0, 2, a foci at 0, negative 3, and 0, 3. So let's plot these. We've got vertex at 0, 2. We'll label this as V1. Foci at 0, negative 3, and 0, positive 3. So this one will be F1, this will be F2. Now we know the center has to be the midpoint between the focuses, so the center must be 0, 0, 0. And we can plot the other vertex. If this is 2 units away, it's got to be 2 units away below here. So that would be V2. So this also tells us what A is. The distance from the center to the vertex is A, so A is just 2. And we also know C is the distance from the center to the focus, which is 3. If we have A and C, we can find B, because we know C squared is equal to A squared plus B squared. So that means that B would equal the square root of C squared minus A squared. So if we put everything in, that's going to be 9 minus 4. So once again, our favorite number here, square root of 5, so that's approximately 2.24. Okay, so let's find the equation. So actually we're not going to end up needing this, but to get the equation, we can see that the transverse axis is the y-axis, which means that we have to use the equation y squared over a squared plus x squared over b squared is equal to 1. Oops, sorry, not plus, that would be an ellipse. Should be minus there. The important thing is the y term has to be first. And we have all the information, we just need to put it in. So our equation will be y squared over 4 minus x squared over, if we square this, we'll just have a 5 there, equals 1. Alright, so we have the equation, now we need to graph it. In order to graph it, we will need to get some other points. So we're going to plug the foci into this, and we're plugging in the y value. So if y is equal to either positive or negative 3, what do we get for x? Well, we're going to have 9 over 4 when we plug the y in here, minus x squared over 5 is equal to 1. In all the other examples, I've been multiplying by the denominators here. Let's do this one without that, so because you don't technically have to do that, and some of you may prefer not to. I'm going to subtract this over, so 1 minus 9/4. Okay, so that will give us negative x squared over 5 equals, common denominator would be 4, so this is negative 5/4. Then I would multiply the 5 over, so I would have, let's move it up a little, I would have negative x squared equals negative 25 over 4. Cancel the negatives, x squared will equal 25 over 4. Take a square root, x will equal plus or minus the square root of 25 over 4, which we've seen this before. They are both perfect squares, so that's plus or minus 5 over 2, or plus or minus 2.5. So this is giving us 4 points here. This is saying that if the y value is plus or minus 3, the x value is plus or minus 2.5. Alright, so let's plot those. Go up to the 3, go over 2.5, go over 2.5 the other direction, and we can do that down below as well. Alright, and then we're ready to plot those points. Okay, for this particular example, I would want these labeled, so we'll just label one of them. This is 3 5/2, but you could label the other ones as well, since they're not on grid points. Okay, did not actually say analyze, so we don't have to write down all of the other pieces, but we've got it graphed, got everything labeled in there, so that should be good for this example. Okay, so in all the examples we've done up to this point, we've graphed and we've gotten our additional points by just plugging numbers in. It would be nice to be able to graph without that, and there is a way to do that, and that is by using what are called the asymptotes of the hyperbola. There are 2 lines that the branches of the hyperbola become infinitely close to as it moves further and further away from the center here. So let's try to figure out how we could get equations for those. So I've just put in the graph of a hyperbola here, and I've labeled a couple things. So the first thing I've done is I put a circle at the origin, centered at the origin, and that circle, its radius, goes out to a focus. We know the distance from the center to the focus is c. That's the coordinates for that focus. And then we know that the distance from the center to the vertex is a. So all of that's consistent with what we've been doing. But if I make that circle, then I can construct a right triangle here. So the way I've constructed the right triangles, I've just made a tangent to the vertex at that point. We know this side is a, we know that this radius has to be the same as this segment right here. They're both radii of the circle. So that means that the hypotenuse of that right triangle has to be C. So the question is, well, what's this? How long is that side there? Well, hopefully you can see it already. That would be a squared plus y squared is equal to c squared. But we already have a relationship for this. We know that we've defined that number to be b, or really b squared. So the height of this triangle is actually b. And that's really where graphically the b comes in. It helps us figure out what these asymptotes are. Now, these are linear equations that pass through the origin. Any line that passes through the origin has the equation y equals m times x, where we have the slope multiplied by x. These are direct variation lines. So the slope is just rise over run. Well, you can count the rise over run out here. For this particular line, we can see it has positive slope, its rise is b, and its run is a. So its slope is simply b over a, and then we would multiply it by x. The one that's on the back side, well, it has the same dimensions. This is still a, and that's still b, but it's going down, so it's a negative slope. It would be negative b over a times x. So that's where these come from. Now, these equations are only going to work when we have the transverse axis being on the x-axis. We're going to see that they get flipped over when the transverse axis is the y-axis up here. Now, one thing to notice too is there's this nice rectangle, and this rectangle is how we're actually going to draw the graphs of the hyperbola from now on. So what we'll do is, once you get the focus, if you know a and b, well, the length of this is 2a, and then we go up b units, down b units, and do that on both sides, make a rectangle, and then you can draw in these asymptotes by drawing in the diagonals. So we'll see that in an example. But before we do that, let's go back and prove a little bit more clearly why the graph has to get infinitely close to this. Right? For right now, it's not obvious why this has to continue to get infinitely close to that. So the argument we're going to use here is technically an argument from calculus. We're going to use a limit type argument, so this is a good preview of some things you'll do in calculus. So I'm starting off with that graph, or the equation of the hyperbola, and what I did through here is I just solved it for y. So I'm not going to bore you with all those steps. If you follow all that algebra, then you get this expression. So this is equivalent to this. Notice we have a plus or minus here because I took the square root of something squared. Okay, so we want to analyze this. And what we want to do is think about what happens if you plug in a really big number to this. For example, let's say you plug in 1 million. Well, if you plug in 1 million to this, that's going to be a big number. That's going to have that 1 million has a big impact on the overall value from this expression. But if you look at this expression, in particular, if you just look at a squared over x squared, if you plug 1 million into that, a squared over 1 million squared, then this is going to be really tiny, very, very small number. And we want to take x to infinity, so we want even bigger than a million. We want 10 million, 100 million, billions. We're going to plug in giant numbers, which means that this expression will approach zero. It will go to zero as x gets bigger and bigger. So in a sense, we can kind of ignore it. It starts to have no impact. So what's left is just the square root of 1. Well, the square root of 1 is 1, which means that as x gets bigger and bigger, this whole piece has no impact. It just behaves like 1, which leaves us with just this. So the point is that this function, or well, really the original function, when x gets bigger and bigger, it will look essentially just like the term in the front here, just like this. And that's why it is the asymptote for that function. Same argument works if you go to negative infinity as well. Okay, so what happens if the transverse axis is the y-axis? When the transverse axis is the y-axis, we're going to use the exact same type of picture. We draw this rectangle where in this case it's the height, but the distance between the vertices is 2a, labeled the same as before, and then the distance we move out in this direction is b on each side, so the length of this is 2b. So the dimensions of this rectangle are the same, but they've been flipped. And since they've been flipped, it ends up flipping the slope. Rise now is A, run is B. And then over here, it would be negative A over B. Now, I don't think it's worth memorizing this. You can if you want. I mean, one way to kind of remember it is remember that the rise always goes with Y. So the number that's below that, or really the square root of the number that's below that, is your rise, and then this is the run. So that is one way to always kind of be able to remember how to get these equations. Okay, so we need to do an example with this. So in order to do that, when we say analyze, we now mean find the center, find the transverse axis, find the vertices, the foci, and the asymptotes. And we're going to use the asymptotes to graph it. So we're no longer going to take the foci and plug it in to get those points out here. We're going to use just the asymptotes. The hyperbola never crosses its asymptotes, so it just gives us a nice kind of gauge to draw it, just draw it really close to those lines, and you get a decent picture from that. Okay, so let's do that with this example. Okay, so notice that this is in the form y squared over a squared minus x squared over b squared equals 1. So a squared is equal to 4, which means a is equal to 2. B squared is equal to 1, so b is equal to 1. If we need c, then c is equal to the square root of a squared plus b squared, which is the square root of 4 plus 1. So once again, our square root of 5, which is approximately 2.24. Let's do center first. Center is still the origin. And transverse axis, the front term tells us that the transverse axis is the y-axis, or the equation x equals 0 if it asked for it in that form. So let's go ahead and plot the center, and we can put in the vertices now. We need to move up 2 units, move down 2 units. Let's go ahead and record them. So 0, 2, and 0, negative 2. We can also do the foci. The C tells us where they are. We're going to move up 2 1/4. So again, these are really close. I didn't really label these. So that's V1. This is going to be F1, V2, F2. All right, so their coordinates would be 0, square root of 5, and 0, negative square root of 5. Okay, so we've got all of that. Now we want to put in the asymptotes. So in order to do that, I'm going to switch my color here. We're going to draw in a rectangle. The rectangle, one dimension is just the distance between the vertices, that's 2a, and then this horizontal dimension is going to be 2 times b. So in this case, we're going to go over 1 unit on each side. That go b units to the right and b units to the left. And we're going to just draw in this rectangle. You technically should be drawing it as like dashed segments. It's not really part of the graph. It's too hard for me to draw them in dashed here, so I'm going to just use different colors when I do that. Okay, so then this rectangle defines the asymptotes. So we can just draw in the diagonals to get the graphs of the asymptotes. So I'm going to use a straight edge to do that. So just connect the diagonals there, draw those in. And again, these should technically be drawn as dashed lines. All right, let's put in the other one then. Okay, so that gives us our asymptotes. Move my ruler out of the way. And so then the idea is the graph of the hyperbola should just get really close to these 2 lines. You shouldn't cross it, but you should just get up next to it. And I kind of touched it there, but should just stay locked between those. And should be symmetric on each side. But so the actual graph then would just be what you see in the blue, but the asymptotes help us get a better representation of that. Okay, so now we need to write down the equation of them. So we know that their equation is just going to be y equals, it'll be plus or minus because they have just negative slopes of each other. And then we can just look at the rectangle, rise over run, which would be 2 over 1 times x. So y equals plus or minus 2x. Those are the asymptotes. And I think put that all together, that's everything that we needed to analyze it. Center, transverse axis, vertices, foci, and now the asymptotes. Okay, let's try another one. So this is another example where it's not currently in standard form. So we need these coefficients to be 1s, and we need this number to be a 1. So we can make that happen by just dividing all of the terms by 36. So that'll make the first one x squared over 4 minus y squared over 9 equals 1. Okay, so that tells us a is the square root of this, which is 2. B is the square root of this, which is 3. So C is the square root of a squared plus b squared, so 4 plus 9, which is the square root of 13. And that is approximately 3.6. Okay, so given the structure that this is in, we know that the center is still the origin. We know that the vertices, actually let's do transverse axis first. So notice it leads with an x, which means transverse axis is going this way. So transverse axis is the x-axis, or y equals 0. And so put in the center, the a tells us the distance to the vertices. So we have vertices at 2 and -2. Call that v1, call this v2. And so let's write those down. And the c value tells us where the foci are. So we need to go over 3.6 and back 3.6. Call this one f1, call that f2. So foci are, we'll use the exact value here, so negative radical 13, 0, and square root of 13, 0. And now we can put in our rectangle. So the dimensions of the rectangle are, we use a and b, so it would be 4 units this way, 2 times a, but then we would go up b and down b. So we need to go up 3 units and down 3 units, up 3 units and down 3 units. Make sure you're doing this along the vertices here. So this is that rectangle that we use to get the asymptotes. And once again, you would be drawing that as a dashed line, just lightly drawn in as a dashed line. Then we can connect the diagonals. Okay, so we have that. Then once you have all that, you can actually go straight to graphing. So we're graphing now in these 2 regions, and we're just going to try to make the graph get close to the asymptotes as it moves out, trying to make it symmetric on both sides. Okay, so again, the blue should be the graph that of the hyperbola, and all of this was just there to help us construct it. Last thing we have to do is asymptotes. So you notice I don't really even worry about the B or the A, I just look at the picture to determine what the asymptotes are. So it's going to be plus or minus rise over run, which is the rise is 3, the run is 2, so the asymptotes are y equals plus or minus 3/2 x. Alright, I think that's it for this one. So let's move on to the next one. So the last examples we want to look at hyperbolas where the center is not at the origin. And this is going to work the same way that it did for all of the other equations. So again, if we take it back to a circle, we said the circle centered at the origin was x squared plus y squared equals r squared. And when we shifted the center, we just replaced x by x minus h squared, replaced the y by y minus k squared. And that was the equation of a circle at a different center. The same thing is going to work for a hyperbola. If we want to shift the center, we just replace x by x minus h, replace the y by y minus k. So you see both of those, both of those forms based on where the transverse axis is, but it's still going to work the same way. You got to be careful with this one because we have the k at the beginning, so that just is easy to mess that one up, but it is still consistent. They're both doing the same type of thing there. Now this also affects our horizontal or our asymptotes to the parabola. And so to write down the formulas for this, it's handy for us to remember point slope form. So point slope form was the form for a linear equation that you didn't use as much in Algebra 1, but I tried to get you converted to in geometry. So if you recall, we wrote that as y minus probably y sub 1 equals m times x minus x sub 1. This was point slope form. So the idea was if you knew the slope, you'd just plug it in there, and if you knew any point that the line passed through, you'd plug it into those 2 points there. So that's where these are actually coming from. The idea is we know that the asymptotes always go through the center hk. So we can go y minus k equals m times x minus h. Just use the center point as the point that the lines pass through. And then the slope will again still be determined by this rectangle. So in this particular example, this is the a and this is the b, so the slope here is the a over b. Whereas in this picture, this is the a and this is the b, so the slope would be b over a. So that's where the two different slopes are coming from. But these are just point slope form. And I believe you're allowed to leave it in that form, even on MathXL. I could be wrong, but I think MathXL takes that form as well. So let's try one of these. Okay, so we've got to find the equation of a hyperbola with the center at 1, -2, a focus at 4, -2, and a vertex at 3, -2. So if we plot this point, 1, -2, that's our center. We have a focus at 4, -2. Let's label that. And a vertex at 3, -2. Now the distance between the center and the vertex is a, and the distance between the center and the focus is c. So we know immediately a is equal to 2 and c is equal to 3. We can find b using the fact that c squared is equal to a squared plus b squared, as it has been for every problem. So b is equal to the square root of c squared minus a squared, which would be square root of 9 minus 4, and what do you know, once again, square root of 5. Okay, so this enables us to put in those other points. So let's go ahead and put in our other vertex. We have a vertex that goes back 2 units, so that would be V2, and then go back 3 units for F2. We can also write the equation at this point. So notice that the transverse axis is horizontal. It's not the x-axis anymore, but it's at least horizontal, which means that we have to use the form that starts with x. So we're going to be doing x minus h squared over a squared minus y minus k squared over b squared is equal to 1. And we have all the information to put in there. So we know the center was, let's just write it up here, hk was given to be 1, -2. So it'll be x minus 1 squared over a squared, which will be 4, minus y minus a -2, which will be plus 2, squared over b squared, which if we square b, we just have 5, equals 1. So getting the equation is not hard. You can do that fairly easily. You don't really even need to make a graph to be able to get the equation. Okay, so let's graph it, and we're going to use the asymptotes again. So we would draw our rectangle around these vertex points, and what we need to do is we need to go up b units, and this one's not very pretty. You can see going up b is going to be, we're going to be off on grid points, so we're just going to have to approximate it roughly about here. Go up 2 and about 1/4 units, go down 2 and about 1/4 units, and then connect those. and then get a straight edge, draw in your asymptotes. Okay, so we got the asymptotes in. Now you can go back and connect those. So not really connecting things, I guess, just drawing it so they approach the asymptotes. And so the blue that's left there would actually be the graph of that hyperbola. Now, the problem does not ask us to do the equation of the asymptotes, but I think it would be good to just practice it because I know you're going to have to do that in the homework. So we know that the asymptotes could be written as y minus k equals m times x minus h. Right? Using point slope form, we just need to use the center. Both of those lines pass through the center. We just need to put in what the slope is. So, and technically it's going to be plus or minus because there are two different asymptotes. So let's write them together in one. So this will be x minus a negative 2, which is y plus 2, same thing that you see here, equals, let's leave the slope blank for now, it'll be x minus 1. So to get the slope, just count it out. So for this, it's not pretty. We go up not just 2, and I don't want to use the approximation. This was square root of 5. So the rise was square root of 5, and the run is 2. And since there were two of them, there's the positive slope one and the negative slope one. These would be your asymptotes. So that's how that would work. All right, let's see if there's another one. Okay, so this next one is particularly nasty. It's given to us in general form. So the first thing that we have to do is put it in standard form. In order to do that, we're going to have to complete the square. And that means we're going to have to complete the square twice. So I'm going to complete the square on the x squared term first. In order to do that, I need a coefficient of 1. So I'm going to start by multiplying everything by a negative, and then I'm also going to bring the x terms to the front. So this will become x squared plus 2x, because I multiplied by a negative. Then I'm going to put plus, leave a blank. I have to multiply that term by a negative, so it's now minus 4y squared plus 16y, because again I multiplied by a negative. And then I'm going to do two things here, not usually recommended, but I multiplied this by a negative, but then I also move it to the other side. So that means it will just be a positive 11 on that other side. Imagine if I had subtracted it over at the beginning, it'd be negative 11, multiply it by negative, it's now positive 11. Okay, we want to complete the square. So we take the b term right here, we divide it by 2, 2 over 2, and then we square it. Well, that's just going to be 1 squared, which is 1. So we're adding 1, but that means we got to add 1 here as well. Go ahead and factor that. So it's x plus 1 all squared minus 4y squared plus 16y equals 12. We now want to complete the square on this part, but in order to do that, we need a coefficient of 1. So to do that, we're going to divide everything by a negative 4. I'm dividing by a negative because I need that to be a coefficient of a positive 1. So that's going to give me x plus 1 squared over negative 4, because I got to divide that by a negative, plus y squared minus 4y, divided that by the negative 4. I'm going to have my blank here, and then I also have to divide that by negative 4, so I get negative 3. Okay, so now we do the same thing here. We do take the negative 4, divide it by 2, square it, so that's just going to give us 4 again. So we have to add 4 on both sides. Right, just make sure you're doing that on both sides, otherwise it wouldn't be an equation anymore, or it wouldn't be balanced. Okay, this should factor, so we're going to leave this one how it was. One thing I am going to do, we don't like negatives in the denominator, so I'm going to go ahead and just pull that out in front of that. And then this becomes y minus 2 squared. And over here we get 1. Okay, this is now actually in standard form. If we order it the appropriate way, meaning that we want the first term to be the positive term, so that means y has to actually be the first one. So that'll be y minus 2 squared minus x plus 1 squared over 4 equals 1. So tedious, but we're now in standard form. Okay, so what can we tell from this? Well, we know that the a, which is really a squared, which is what's under this, is 1. So that means a is 1. B squared is 4, which means b is 2. And c is equal to the square root of a squared plus b squared. So that would be the square root of 1 plus 4. So once again, square root of 5. All right, so we have the a, b, and c. Let's double check to make sure that we need all of this. Okay, it does say analyze, so yeah, we've got to do all the parts for this. I'm going to move this down. Okay, so center. We know the center is HK. And in this problem, H is -1. It's -1 because the normal formula has a minus sign built in here. And then the K would just be +2. Let's go ahead and plot that too. So -1, -1, 2 is here. We also know that since the y term is the first term, the transverse axis has to be vertical. But the transverse axis is not the y-axis, it's actually this vertical line, so it would be x equals -1. Right, running vertically like that, x equals -1. Okay, we said a is 1, which means to get to our vertices, we just need to go up and up 1 and down 1. To get to the foci, we need to go up 2.24 approximately, so we'll go up about 2 1/4 from the center. All right, so that'll be F1, and this can be F2. If we write down the coordinates for those, I guess we should do vertices first. Then foci. All right, so here's where we got to be careful. So we are going up square root of 5 from that point. So the x is still -1, but the y value is going to be 2 plus the square root of 5. So 2 plus square root of 5. And then -1, and this one is 2 minus the square root of 5. Okay, so before we do the asymptotes, I usually like to graph it. So in order to graph it, we're going to put in the box. So we start at the vertices, and this distance is 2a. We need to go horizontally b units, so 2 units to the right, 2 units to the left, 2 units to the right, 2 units to the left. Draw in your rectangle. And then get a straight edge and draw in your asymptotes. Okay, so now we can connect the points, or make the graph approach the asymptote, I should say. And there we have it. I think, oh, we still need the asymptotes. Yes, we got to write the equation of those. So as before, they're going to be in the form y minus k equals technically plus or minus m times x minus h, where the h and the k are the center. So y, what do we got for h, is -2 equals plus or minus, we'll put in the slope in a second, x plus 1. Okay, so to get the slope, you just look at the picture. It's rise 1, run 2. So it looks like plus or minus 1/2. So those are the asymptotes. And that, together with this, and our equation, should be everything that they asked for. So you can see these are quite a bit more work. I guess we should label these in the picture as well, but we've got it labeled over here. Okay, so to finish things, we're going to look at some applications. So let's look at a generalization of what we'll do in the last problem here. So suppose you have 3 microphones. They're located at 3 different points. These O's are where the microphones are at, so O1, O2, and O3. And suppose there is a gun that's fired, and the gun is fired at this location here. Now, sound does not travel instantaneously, so it's going to take a certain amount of time for it to travel to each of these microphones. And one way to kind of think about that is, let me get back to say I draw a circle of this radius about that point. Okay, so there's my circle. So the idea is that anything on this circle, the sound will be heard at the exact same time. If you're standing here, or if you're standing over here, all those places will hear the sound at the same time. So notice this place here is going to hear the sound after this microphone hears it. So let's make the assumption that it hears it 1 second after this one. Neither one of them are hearing it instantaneously. They both have to wait a certain amount of time, but 01, they have to wait 1 second longer. Now suppose that we also know that sound can travel about 1100 feet per second. Well, that means if they hear it 1 second later, that this segment right here has to be 1100 feet, because that was the additional distance it had to travel. Another way to characterize this is if we take the segment S01 and we subtract the segment S02, that is 1100. That's actually exactly what this segment represents. It represents the distance between the difference between those two segments. Now, because we are subtracting two distances, that means we could model these 2 points using a hyperbola. What we could think of is we could think of them as being the foci of a hyperbola, and these black branches are representing the hyperbola, where these 2 points are the focus, and this is a point on that hyperbola. So it's, and technically any point, if I pick anything, let's say I pick this point here, and I take this segment and I subtract that segment, I'm always going to get this 1100. Right? That's what every point represents. One way to think about it is if you were to keep shooting a gun, and you were to shoot it here, and you were to shoot it here, and you were to shoot it here, at every single point on that curve, every single time you shot the gun, this microphone would hear it 1 second after this. But if you moved off of that line, then the time delay is not going to be 1 second. These are the only places where the time delay is 1 second. Now, the reason for the other branch, which we're not actually going to use on this, but this branch would represent when this hears it 1 second after this microphone over here. Okay, now imagine that there's a third microphone, and that third microphone hears it 2 seconds after this microphone. Well, we could use the same type of reasoning, that these 2 points are the foci of a hyperbola, and that the point S is a point on one of the branches of the hyperbola, but in this case the difference between them is 2200, because it was 2 seconds after. So we could write down the formula then for this hyperbola. So we have the formula for the first hyperbola, formula for the second hyperbola, and then to actually figure out exactly where S is located, we would just solve that system. We actually did problems like this back in college algebra when we solved nonlinear systems. We just didn't have to set up the hyperbolas at the beginning. So this concept is actually used. In some cities, they set up in areas where there's lots of crime and people don't report the crime, they will set up sometimes listening devices, microphones, and they can then triangulate the location just based off of the sound. And this is essentially how that could work. Okay, let's try an example. So it says, suppose that 2 people standing 1 mile apart both see a flash of lightning. After a period of time, the person standing at point A, over here, hears the thunder, and then 1 second later, the person standing at point B, this person, hears the thunder. If the person at point B is due west of the person at point A, and the lightning strike is known to occur due north of the person standing at A, where did the lightning strike occur? Now, this problem has some special conditions that make it much easier to solve than the example I explained before. And the main thing being that we know that the lightning was directly north of the person at A. That's really what makes this much simpler. Okay, so we've modeled this with a hyperbola centered at the origin. It said that the 2 people are 1 mile apart from each other. So that's the distance between each of the foci is 1 mile. So I've labeled that as 5,280. And we also know that we could then put coordinates on these. So the A point could be, it's just half of 5,280. Same thing for the B. So the first thing to notice is the distance between the center and a focus is C. So we know the value of C is 2,640. The other thing that we know is that the lightning had to have occurred on a branch of a hyperbola. So if we represent this point, let's say as P, then the distance PB minus the distance PA has to be the constant difference. So this segment minus this segment has to be the constant distance, which is always 2a. But we know what this difference is. We know that it's there's 1 second delay between them, so that means that this has to be 1100. Just like the previous example, we're assuming sound travels at 1100 feet per second, so 1100 would have to equal 2a, which then tells us our a is actually 550. So we have A, we have C, we can get B by using the fact that C squared is equal to A squared plus B squared. So B is going to be, let's not do B, we really only need B squared because we're going to be plugging it into the formula. So B squared is just C squared minus A squared. It's just 2,640 minus squared minus 550 squared, which comes out to the big number of 6,667,100. All right, so then we know we designed this so that the center is at the origin and the transverse axis is the x-axis, which means that our hyperbola has to have this form. Has to start with the x because the transverse axis is the x-axis. It's equal to 1. And we have all the information now, so we can write it in here. So it's going to be x squared over 550 squared. I'm just going to leave it with the square on it, minus y squared over b squared. We don't need to square this. It's already squared. So we just write 6,667,100 on the bottom of that equals 1. Okay, this models this blue hyperbola. So what we want to know is we just want to find that distance there. So to find that distance, all we need to do is plug in this point. Plug in not the y, we just need to plug in the x coordinate and get the y coordinate. So plug in 2,640 for the x, so 2,640 squared over 550 squared minus y squared over 6,667,100 equals 1. All right, we're going to solve this without actually simplifying all that. We would subtract this over, then we would multiply by this big number here. We could multiply by a negative, which would just flip this around, and then take a square root. That could be put in your calculator and comes out approximately to, actually I think it comes out exact, to 12,122 feet, or approximately 2.296 miles. So that represents this vertical distance right here. Right, we plugged in 2,640 into our formula, and we got that that was 12,122 feet. All right, this is a long set of notes, very technical, so hopefully this was helpful. If you're having issues with the homework, make sure you're emailing me, and we will see you guys in the next video.